Hi, my name is Doron Chen and I'm going to present our work on length-preserving compression. This is joint work with Michael Factor, Dani Harnik, Ronen Kat, and Eliad Tzfadia. The term length-preserving and the word compression appear to be contradictory, but we present a use case in which they go hand in hand. The term length-preserving compression is inspired by the term length-preserving encryption, which refers to encryption methods for which the ciphertext is the same length as the plain text. For block storage, length-preserving encryption is extremely desirable since it does not interfere with the data layout. Length-preserving compression is similarly designed to avoid changing data layout. Before I explain what length-preserving compression is, let me first explain the motivation for our work through a true story. A large company noticed that once it began encrypting its data, the storage expenses immediately ballooned. Why would encryption have that effect? The reason is that many storage systems come with built-in data reduction capabilities. When you take compressible data and encrypt it, you transform it into pseudo-random data which is totally incompressible. If your data is 3x compressible, once you begin to encrypt it, you need 3 times the amount of storage. The problem we are trying to solve is how to combine end-to-end encryption with compression. Let's set compression aside for a moment and let's talk about end-to-end encryption. The idea of end-to-end encryption is for the data to be encrypted at all times from the moment it leaves the host. This is often mandated by regulatory demands such as HIPAA or GDPR. Having data encrypted at all times is especially important when data is in the cloud on infrastructure which is shared across multiple tenants and is managed by an outside party, which is the cloud provider. What are the options for encrypting stored data? We can use data at rest encryption at the storage, which leaves the data in the clear over the network and in the storage controller. We can also add in-flight encryption, so that the data is encrypted on the host, decrypted on the storage, and then re-encrypted. Neither of these options constitutes true end-to-end encryption, since the storage system has access to the unencrypted data. If we use one of these two options, the storage controller can access the unencrypted data and therefore has the opportunity to compress it before encryption. True end-to-end encryption, which is the focus of our work, refers to application, hypervisor, or OS-level encryption. What all these approaches have in common is that the data is never in the clear except at the host. However, these solutions appear to eliminate the opportunities for storage-side data reduction. So, if compression after encryption is impossible, how about we compress the data first at the host and only then encrypt it? This is problematic since compression, by definition, changes the length of the data. This may not be too problematic if we wish to access the data sequentially. But suppose we wish to access the data randomly, or we wish to support writes as well as reads. If the compression is done at the host, then it becomes the host's responsibility to maintain the data structures that map logical and physical sectors. This is a complex task which requires significant resources. A task that is typically handled at the storage side by advanced storage systems. We'll get back to it a bit later, but first let us introduce the method that we are proposing, length-preserving compression, or LPC in short. LPC, like standard encryption for block storage, works at a sector level, one sector at a time. The basic idea is very simple. Compress a data sector at the host, encrypt the compressed portion, add some metadata, and then pad the encrypted data back to its original sector size with a highly compressible padding such as zeros. This constitutes a length-preserving transformation as desired. Our method also needs to address incompressible sectors. Such data actually inflates slightly when we attempt to compress it. What we do is, for each sector, we first try to compress it. we set a threshold, for instance 32 bytes. If we cannot save at least 32 bytes, we skip compression altogether and proceed only with encryption. If compressing the sector saves at least 32 bytes, we proceed as in this figure. Since we use 2 bytes for metadata, this green portion over here, we know that any compressible sector is transformed into a sector which ends with at least 30 bytes. This helps us differentiate between compressible and incompressible sectors. So, how does the read operation work? We begin by looking at the final 30 bytes. If they are not a 30-byte zero sequence, then they surely represent an incompressible sector, in which case we simply apply decryption to that sector. If the final 30 bytes are a sequence of zeros, then we treat the sector as a compressed sector. We decrypt the compressed portion and then decompress it. Of course, there is a chance that an encrypted sector, which contains pseudo-random bytes, just happens to end with 30 bytes or 240 bits. However, that chance is 1 over 2 to the power of 240, which is a chance so infinitesimally small that we could not find a proper analogy for it. The chance is essentially 0. This was LPC on a single sector. Let's see what it looks like on a bunch of sectors. Here we have 6 sectors with different levels of compressibility. Some are highly compressible, some are moderately compressible, and some are totally incompressible. Note that, true to its name, LPC preserves the lengths of all of these sectors. These white portions are zero sequences. These zero sequences can be reduced by any storage system that supports compression, thereby achieving compression gains despite the encryption. LPC offers significant benefits. It allows the host to compress in a stateless manner with no need to manage data mappings. It supports multiple hosts working on the same data. It requires no changes from the storage stack or the storage protocol and works transparently with any storage that has the ability to compress zero sequences. The storage is not aware of the fact that data is compressed or encrypted. Finally, it achieves this without compromising our main goal of end-to-end encryption. The data is never in the clear outside the host. LPC also has some potentially negative implications. It adds performance overhead at the host compared to host-side encryption with no compression. It has a small impact on compression savings compared to storage-side compression with no encryption. And it leaks compressibility data compared to host-side encryption with no compression. We will later discuss each of these topics in greater detail. Let us compare LPC to other approaches for which compression is done at the host. If the compression is not length preserving, then the host must handle the variable size data layout. Managing storage with variable size is a tough problem, which the storage systems have already put a lot of work into. Adding such capabilities to the host as well is very expensive in terms of performance overhead and RAM requirements. It also complicates scenarios where there are multiple hosts using the same storage pool. Whenever one host writes to storage, it must trigger mechanisms that update the mappings between logical and physical sectors in all other hosts. All of this is avoided when keeping the length of writes unmodified, as we do with LPC. Let's get back to discussing the implications of using LPC. We begin with the performance overhead at the host. To evaluate the performance overhead, we ran tests on 2 LPC implementations. One is the dm-crypt disk encryption model, and the other is the Zen blktap disk I/O interface. We used LZ4 as our compression engine because it is relatively high performance, and AES XTS encryption. We compare LPC performance at the host versus encryption with no compression. Before I show you some results, here is a list of our main observations. LPC adds an overhead above standard encryption since it adds a compression operation to the encryption. Compression is generally a more expensive operation than encryption. However, The effect of this overhead only becomes a bottleneck when running high-performance workloads on high-performance storage. We tested LPC on both 4K sectors and 512-byte sectors. We found that performance on 4K sectors is significantly better than on 512-byte sectors. This is due to the fact that initializing the compression engine for each new sector is expensive. We found that LPC read performance is excellent across all tests and significantly better than LPC write performance. That is because the price of LZ4 compression is much higher than that of decompression. Interestingly, LPC write performance is worse for moderately compressible data compared to highly compressible and incompressible data. This mirrors the performance behavior of the LZ4 compression engine. Latency. The following graphs show the latency of LPC versus regular encryption on an SSD drive as a function of the IOPS. We tested LPC with 4K sectors and with 512-byte sectors. The bottom graphs show regular encryption and LPC performance on incompressible and on highly compressible data. The performances of these two cases are very similar. In red, you see LPC latency when we run LPC on 512-byte sectors. If you look at the light blue line over here, you see that LPC latency is only slightly above that of regular encryption. This is particularly true for incompressible and highly compressible sectors. For moderately compressible sectors, the latency is a bit higher. In terms of CPU utilization, once again, LPC on 4K sectors is comparable to that of regular encryption, particularly for incompressible and highly compressible sectors. For moderately compressible sectors, the CPU utilization is a bit higher. You can find more information on LPC performance in the paper. Now, let's discuss the lower compression savings compared to storage-side compression with no encryption. LPC achieves lower compression ratios than the potential compression ratios that a storage system could gain. There are a number of reasons for this. We use a relatively fast compressor which sacrifices minor compression gains compared to, for example, zlib. With LPC, we are forced to work with relatively small compression blocks. Compression algorithms are based on finding repetitions in the data streams, and there are less opportunities to find such repetitions when data is sliced into small compression blocks. When it comes to compression savings, once again, LPC on 4K sectors is better than 512-byte sectors. This is demonstrated in this table, which shows LPC compression savings versus the compressibility potential on various types of data. The basic LPC design only addresses compression savings and not deduplication savings. In the paper, we suggest how LPC can be modified to also allow potential deduplication savings. Finally, we need to address security implications. LPC leaks information regarding the data compressibility compared to host-side encryption with no compression. For example, an adversary might be able to guess with high probability what language the data is written in. LPC may also leak the existence of data duplication information or lack thereof. We note, however, that any method in which compression savings are achieved must leak some information about the data compressibility. LPC still ensures that data is always encrypted, and without strong prior knowledge about the data, there is very little that one can learn. In the paper, we give an in-depth discussion of the security that LPC guarantees and ways to mitigate some of the leakage of compressibility information. In conclusion, we present a host-side method that supports end-to-end host-side encryption while still leveraging built-in compression capabilities which are integrated into many modern storage systems. We view LPC as a sensible trade-off between space savings and full end-to-end security. LPC is simple to deploy, works seamlessly with existing storage systems, and requires no changes to the storage protocol, making it very attractive to use in existing deployments. Thank you.
Thank you. That was a very interesting talk. And while we wait for questions from the audience, I have a question of my own to ask. So you talked about the compression ratios, but so you apply padding to a sector after it has been compressed and encrypted, right? To bring back the size of the data to the size of the sector. So in that sense, I mean, the any extra space in the sector after the compression has been applied is not usable for any other data. Is that correct? So is there any actual saving in terms of the storage space, or am I missing something here?
So the idea is to use the built-in mechanisms for data compression within the storage system. So if you have even relatively short sequences of zeros, then the storage system knows what to do with them in order to save space.
Okay, I see. And so another question is, would it be possible to combine LPC with a file system as well on top of the storage?
So basically, you can apply it anywhere where you need the possibility to access the data randomly. So it can be used in the file system as well. It can be used in block storage. You are not really limited in where you need to apply it.
Okay. So we have one question from the audience. Yitzhak?
Yeah, question. Can this be combined with deduplication?
Yes. So we addressed this in the paper. So we can use the convergent encryption in order to make sure that identical sectors are transformed into identical encrypted sectors. So usually the problem with the convergent encryption is that it requires more metadata, and you need a place to store it, which is not length preserving. But here, since we have the compression, we can use some of the space we should allocate for metadata in order to store the initialization vectors. So we do describe how it can be used alongside with deduplication to gain some further space savings. I should say that the savings don't work when you use different keys. So if it will work within the same volume or across volumes which use the same keys, but if different volumes use different keys, you cannot gain space saving from deduplication.
Okay, thank you.
We have one more question from Eris. Eris, would you like to ask yourself?
Sure. Hi, Doron.
Hi.
You know, I like this work because I've done storage compression file systems and looked at these kind of size changing things. I'm wondering if you have a way to configure the compression algorithms based on the entropy of the data and even turn it off if the data itself is already pre-compressed, like an MP3 stream. Have you thought about that?
I have not. Maybe Danny has thoughts on this matter. Danny, are you there?
Yeah, I'm here. Just a small thing that we can do. I mean, basically, you can try and compress with various ways. We keep a bit of metadata in each chunk. So potentially you can have a mix of any type of compression. Each block, like each 4K uses the different method altogether. It can still work. And of course, if you choose not to compress, that's fine. One of the nice things is that data that is not compressed does not change at all. So it's also backward compatible if you just bring in data that was never compressed. So it's on a block by block basis. You can do whatever you want. But like Doron said, we haven't toyed with anything of that sort.
Okay, cool. Thank you.